Section 4.8 is on complex numbers. All real numbers are a subset of a larger set of numbers called complex numbers. All complex numbers are either real or imaginary. Imaginary numbers use the imaginary unit I. I is the number whose square is -1. That is, I squared is equal to -1, so I is equal to the square root of -1. This is how we're going to deal with taking the square root of a negative number. So just to summarize here, so for any positive number a, if we're taking the square root of -a, we're going to rewrite that as the square root of -1 times a, which is the square root of -1, which is I, times the square root of a, so we would get I times the square root of a. Here's an example using a -5. Now notice that when you square a negative square root, okay, so that's going to be the same as, so the square root of -5 squared is I times the square root of 5 squared. I squared is -1, square root of 5 squared is 5, so that's equal to a -5. Let's take a look at an example. So here we need to simplify the square root of -24 using the imaginary unit I. So the first thing I'm going to do is rewrite the square root of -24 as the square root of -1. And now I have to simplify square root of 24. I'm going to write that as the square root of 4 times the square root of 6. So square root of -1 becomes I. Square root of 4 is 2. Square root of 6 can't be simplified, so that stays square root of 6. So that's going to give me 2I times the square root of 6. And that's generally how we write it. We almost write I as though it were a variable, although it is not. So here's a summary from your textbook of complex numbers. Oh, actually, so an imaginary number is any number in the form a plus bi, where a and b are real numbers and b is not equal to 0. So I really like this chart here. So here we have all the complex numbers, and that's all of the numbers that we know. Of the real numbers are actually a part of complex when b is equal to 0. So if this were like 3 plus 0i, well, 0 times I is 0, so that would be just 3, which is a real number that we're familiar with. Then the other part of the complex number universe is imaginary numbers where you have a plus bi, where b is not equal to 0, so something like 3 plus 2i. And then pure imaginary numbers are where a is equal to 0, so you might have something just like 3i. In the complex number plane, the point AB represents the complex number a plus bi. The horizontal axis is the real part of the number, and the vertical axis is the imaginary part. The absolute value of a complex number is its distance from the origin in the complex plane. So the absolute value of a plus bi is equal to the square root of a squared plus b squared, which you'll notice is basically the Pythagorean theorem, which makes sense. Let's take a look at an example here. So we have to plot each number and find its absolute value. So number 1 is 1 minus 3i. So for this, a is 1 and b is -3. So really, instead of x and y here, I should have that this is the real axis, which is our a. This is my imaginary axis, which is going to be my b. So to plot the complex number 1 minus 3i, I would go 1 for the real and -3 for the imaginary, so that would be this point right here. And I'll just label that. That's number 1. Now, to find its absolute value, so the absolute value of 1 minus 3i is equal to the square root of a squared plus b squared, which is the square root of 1 plus 9, or the square root of 10, which would actually be the distance from the origin to that point that I plotted. Let's do number 2 here. So I have the complex number -4 plus i, so a is equal to -4, and my b is equal to 1 since there's not a number in front of i, so that would be -4 on the real axis and up 1 on the imaginary axis, so that would be that point right there. Now to find its absolute value, so the absolute value of -4 plus I is equal to the square root of a squared, which is -4, plus 1 squared. -4 squared is 16, plus 1 or its absolute value, is the square root of 17. So to add or subtract complex numbers, we want to combine the real parts, so the a parts, and the imaginary parts separately. That's the bi parts. To multiply two complex numbers, we're going to use the distributive property. So let's take a look at several examples here. I need to simplify each expression. Number 1 says 2 plus I plus negative 3 plus 3I. So I'm going to combine my real parts. So that's going to give me a negative 1. And then I combine my imaginary parts. I plus 3I gives me 4I. So negative 1 plus 4I. Subtracting is similar, but it's a little different because this is really kind of like a negative 1 that I have to distribute to each one of those. So I'm going to rewrite this as negative 6 minus 2I minus 4 minus 2I. Now again, I combine my real parts, so that's going to give me a negative 10. And then I combine my imaginary parts, and that's going to give me a negative 4I. Now, to multiply, I'm going to use the distributive property. So here I need to distribute a negative I to each one of those terms. So that's going to give me a negative 4I plus 8I squared. A negative times a negative gives me a positive. I times I is I squared. Now remember, I squared is negative 1. So this is the same as negative 4I plus 8 times negative 1, or putting in the format a plus bi, negative 8 minus 4I. And here we have what looks like two binomials, and we're going to distribute, basically we're going to FOIL. So when I do my first, I'm going to get a negative 20. And I do my outer, I'm going to get a negative 15I. I'll do my inner, positive 28I. And my last is going to give me a positive 21I squared. So let's clean that up a little bit. Negative 20 plus 13I. And remember, I squared, this right here, is a negative 1. So then this is really minus 21. So that leaves me with a negative 41 plus 13I as my final answer. Now, when we're dividing complex numbers, we cannot have a complex number in the denominator. So to simplify, we're going to multiply by what's called its complex conjugate. So if I have a plus bi, its complex conjugate is a minus bi. And when I FOIL these two, it's going to eliminate the I because it looks kind of like a difference of squares. It actually ends up being a sum of squares. But a plus bi times a minus bi is a squared plus b squared. So notice what's going to happen. So this is going to give me a positive abi. This is going to give me a negative abi, so that cancels the i's out there. But now when I do my last, I'm going to have a negative b squared times I squared. Remember, I squared is negative 1, so that's the same as negative b squared times a negative 1, which is going to give me my plus b squared. Okay, bottom line is this is how we're going to get rid of having a complex number in the denominator. So let's take a look at a couple examples here. So I have 7I divided by 8 plus I. So I'm going to multiply top and bottom times 8 minus I over 8 minus I. On top, when I distribute, that's going to give me 56I minus 7I squared. I'll clean that up in a minute. And I'm just going to use the shortcut here, and I'm just going to do my first and my last. That's going to give me 64 minus I squared. On top, remember I squared is negative 1, so that's going to make that a positive 7. So 7 plus 56I over, this is going to turn into 64 plus 1, so minus a negative 1, or 65. Let's take a look at our second example here. 5 plus 2I over 3 minus 2I, so multiplying by the complex conjugate, 3 plus 2I. over 3 plus 2i. I need to FOIL on the top. 15 plus 10i plus 6i plus 4i squared. And then on the bottom, when I do my first, I get 9. When I do my last, I get minus 4i squared. Let's clean this up. This is going to turn into a minus 4 because remember I squared is negative 1. So that's going to give me 11 plus 16i over, this is going to turn into a plus 4 over 13. And there's my final answer. Okay, and our last couple examples here, we have to factor 3x squared plus 12. So the first thing I'm noticing is that I can take out a greatest common factor of 3, and that leaves me 3 times the quantity x squared plus 4. And notice that this is a sum of squares. In the past we've dealt with a difference of squares, but this is a sum of squares. And it looks like what we had up above. This looks like a squared plus b squared. And remember, that will factor into a plus bi times a minus bi. And in this case, my a squared is x squared, so a is equal to x. My b squared is 4, so my b is equal to 2. So that part is going to factor into 3 times a plus bi, x plus 2i, and then an a minus bi, x minus 2i. And that's my final answer. And our last problem here, we have to solve the quadratic equation, negative x squared plus 4x minus 5 equals 0. To do this, I'm going to use the quadratic formula. So x is equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Cleaning that up a little bit, negative 4 plus or minus, so this is going to give me 16 minus 20, which is the square root of negative 4 over negative 2, which is negative 4 plus or minus, square root of negative 4 is the square root of negative 1 times the square root of 4, or 2i over negative 2. And now I can do a little canceling here. If I cancel that, it becomes a 1, that becomes a 2, and that becomes a 1. So that leaves me with 2 plus or minus I. Okay? Or if you'd like, you can say x equals 2 plus I and x equals 2 minus I. So in this section, we took a look at a concept that's probably kind of new to you and kind of radical, and that is complex numbers. We learned about the imaginary unit I and the realm of complex numbers, which includes real and imaginary numbers.